Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi there, Herman and Corn. So we've talked about aviation in a number of episodes, and I'd love to ask you about something, again, pretty specific that I've always just kind of wondered about or been in awe of. So we know that fly-by-wire, I believe it was pioneered by Airbus, and the idea being that the control surfaces of the airplane, the ailerons and the wings and the rudder, on the tailplane and the rest, all the control surfaces are linked by wire, and that they have these crazy systems for redundancy, as everything does in aviation. But whatever the opposite of fly-by-wire is, the mechanical system that works in hydraulics. When I read about fly-by-wire, I guess I always just assumed that was how planes work in general. The idea that you could have something as big as a Boeing 737 or 747, and that the connections between, really, when the plane moves, that even if it's through this intricate series of connections, that there's a direct physical link between what the pilot's doing in the cockpit and all the way down to the wings. That seems kind of dangerous to me. So I guess maybe some people would see it the opposite way, that working electronically seems dangerous. But to me, the idea that there would be actually just physical connections, albeit through hydraulics, linking the two, seemed really strange. So I'd love to understand a bit more about that, Herman and Corn. And I don't know, it's been quite a while since I was really a serious aviation geek. But what's happening nowadays? Is fly-by-wire the norm, or do we still see mechanical operations? And what about at that level of scale before fly-by-wire became the standard or a norm? Those huge aircraft that were operated mechanically, how does that even work at that level of scale, like in terms of the amount and number of moving parts between the control surfaces and the actual in the cockpit and the ones on the actual wing? And I'm assuming that there was a bunch of failover systems here, just as there are in every other aspect of aviation. So how do you implement in the fairly tight space of a commercial aircraft, but with all the other systems and avionics going on, how do you even fit such elaborate control systems and failover systems all within that fuselage space? Over to you, Herman and Corn. Let's talk about fly-by-wire versus whatever came before it, or maybe still exists.
Hey everyone, welcome back to My Weird Prompts. I am Corn, and I'm feeling particularly grounded today, which is ironic because we are about to talk about being 30,000 feet in the air. It is February 7th, 2026, and while we are all looking forward to spring, the world of aviation never really stops to catch its breath.
And I am Herman Poppleberry. I have my flight charts, my engineering diagrams, and a very large cup of coffee ready to go. Our housemate Daniel actually sent us a really fantastic prompt this week that hits right at the intersection of mechanical engineering, computer science, and human psychology. It is a deep dive into how we actually steer these massive metal tubes through the sky.
It is a great one. Daniel was asking about the evolution of aircraft control systems. Specifically, he was curious about how we move from physical cables and pulleys to what we call fly-by-wire. And honestly, it is one of those things you do not think about when you are eating your tiny bag of pretzels in seat 14B. But your life literally depends on these systems working perfectly every single second of the flight. If the connection between the pilot's hand and the wing fails, the physics of a 100-ton jet become very unforgiving, very quickly.
It really does. And Daniel mentioned Airbus as the pioneer of fly-by-wire, which is largely true for commercial aviation, but the history goes back even further to military research and even the space program. But he also asked about the mechanical and hydraulic systems that came before it. How do you move a massive rudder on a Boeing 747 using just your hands? It sounds impossible when you think about the wind resistance at 500 miles per hour. We are talking about forces that would snap a human arm like a toothpick if there was a direct, unassisted link.
Right, because if I am stick handling a little paper airplane, it is easy. But if I am trying to move a piece of metal the size of a garage door against a 500-mile-per-hour gale, there has to be some serious physics involved. So, Herman, let us start with the old school. Before the computers took over, how did a pilot actually move the wings? Take us back to the era of grease, steel, and muscle.
So, in the early days, like the Wright brothers era, it was literally cables. The Wright flyer used a system of wires to warp the entire wing structure. It was called wing warping. As planes got bigger and faster, they moved to discrete control surfaces like ailerons, elevators, and rudders. In a classic mechanical system, there is a direct physical connection. You pull the yoke back, a steel cable runs through a series of pulleys through the fuselage, and it physically pulls the elevator up. It is not much different from the brake cable on a bicycle, just much, much longer and under significantly more tension.
And that works fine for a small Cessna, right? I've been in a four-seater where you can see the cables running along the ceiling. I can imagine that being manageable for a human.
Exactly. On a small aircraft, the forces are low enough that human muscle is plenty. We call these reversible controls. You can actually feel the air pushing back on the control surfaces through the yoke. If a gust of wind hits the tail, the yoke might actually twitch in your hand. Pilots love that because it gives them a direct, tactile feel for the state of the air. It is like feeling the road through the steering wheel of a sports car. But as soon as you get to something like a Boeing 707 or an early 727, the air loads become immense. A human simply cannot pull hard enough to overcome the aerodynamic pressure on a large control surface at high speed. Imagine trying to open a car door while you are driving at 60 miles per hour. Now imagine doing that at 500 miles per hour with a door the size of a billboard.
So what was the solution? Did they just hire really buff pilots? Like, was the flight school entrance exam just a bench press competition?
No, though that would be a funny image. They turned to hydraulics. This is what we call hydromechanical systems. Think of it like power steering in your car, but on a massive scale. There is still a cable running from the cockpit to the wing, but instead of the cable pulling the wing directly, the cable moves a small input valve. That valve then directs high-pressure hydraulic fluid into an actuator, which is basically a big metal piston. That piston is what does the heavy lifting to move the aileron or the rudder. The pilot provides the command, and the hydraulic system provides the muscle.
Okay, so the cable is just sending the command, and the hydraulic fluid is providing the muscle. But Daniel asked about the scale. On a Boeing 747, which is a massive double-decker aircraft, how much cable are we talking about? How do you even route that through a plane that is over 200 feet long?
It is staggering, Corn. On those older large jets, you have miles of steel cables. They have to be routed through the entire length of the fuselage, around corners using pulleys, through tensioners to account for the way the airframe stretches and shrinks. This is a detail people often miss. A plane actually grows a few inches in length when it is pressurized at altitude because the fuselage expands like a balloon. If your cables do not have complex tensioners, they would either snap or go slack every time you climbed or descended.
That sounds like a maintenance nightmare. If one pulley gets jammed or one cable starts to fray, you are in big trouble. And Daniel asked about the space. How do you fit all that into the walls of the plane?
It is a huge maintenance burden. Every single pulley needs to be inspected and lubricated, and it is heavy. Steel cables and the heavy brackets to hold them add thousands of pounds to the weight of the aircraft. Plus, you have to have redundancy. Daniel mentioned this in his prompt. In those mechanical days, redundancy meant having multiple separate cable runs. If the left side cables were severed, hopefully the right side ones still worked. But you are still limited by the fact that it is a physical moving part that can wear out. On the Boeing 747, they actually had 4 independent hydraulic systems. They were color-coded and completely separated so that even if an engine exploded and took out one system, the others would keep the plane flying.
So then along comes Airbus in the late 1980s with the A320. This was the big shift, right? Flyby, wire. What actually changed in the cockpit? Was it just getting rid of the cables?
It was a total paradigm shift. In a fly-by-wire system, that physical cable is gone, totally deleted. When the pilot moves the side stick, they are not pulling a wire. They are moving a transducer that converts the physical movement into an electronic signal, a digital 1 or 0. That signal travels through copper wires or fiber optics to a flight control computer. The computer looks at the pilot's input, looks at the current airspeed, the altitude, the angle of the plane, and then calculates exactly how much the wing surface should move. Then it sends an electronic command to the hydraulic actuator at the wing. It is the difference between a manual typewriter and a high-end gaming laptop.
So the computer is the middleman. And this brings us to one of the most controversial and fascinating parts of fly-by-wire, which is flight envelope protection. Because the computer is sitting between the pilot and the wing, the computer can say no.
Exactly. This is the core of the Airbus philosophy. If a pilot tries to pull up so sharply that the plane would stall and fall out of the sky, the Airbus computer will simply refuse to do it. It keeps the plane within a safe envelope. It prevents overstressing the airframe. It makes the plane essentially impossible to stall under normal conditions. This was revolutionary when the A320 launched in 1987. It was the first time a commercial airliner used a full digital fly-by-wire system. Before that, the Concorde used an analog version, and the F-16 fighter jet used it because the F-16 is actually aerodynamically unstable. It needs the computer to make hundreds of tiny adjustments per second just to keep it from tumbling out of the sky.
I remember we talked about this briefly in a previous episode about automation. Airbus and Boeing actually have very different philosophies on this, do they not? Daniel was curious if fly-by-wire is the norm, but it seems like the way it is implemented varies.
They are worlds apart. Airbus believes the computer should have the final say on safety. Their logic is that humans make mistakes under stress, and the computer can prevent those mistakes. Boeing, even as they move toward fly-by-wire with the 777 and the 787, tends to believe the pilot should always be the ultimate authority. On a Boeing, if you pull back hard enough, you can override the soft limits. The yoke even moves on its own to show you what the computer is doing, whereas on an Airbus, the side stick is stationary unless the pilot moves it. It is a fundamental philosophical divide. Is the pilot flying the computer, or is the computer helping the pilot fly?
But back to Daniel's question about whether this is the norm today. If I walk onto a plane today, am I on a fly-by-wire aircraft?
If it is a modern airliner designed in the last 30 years, almost certainly yes. The Airbus A320 family, the A330, A340, A350, and the giant A380 are all fly-by-wire. On the Boeing side, the 777 and the 787 are fly-by-wire. However, there is one huge exception that Daniel specifically mentioned, and it is the most common plane in the sky, the Boeing 737.
Wait, the 737 is still mechanical? Even the new ones? I see those everywhere.
It is a bit of a hybrid, but at its core, the 737 is a legacy design from the 1960s. The primary flight controls, the elevators and ailerons, are still operated by cables and pulleys with hydraulic assistance. Even the newer 737 MAX has cables running through the floor. They have added electronic components. For example, the spoilers are now fly-by-wire, and of course there was the whole MCAS system, which was a digital layer on top of a mechanical system. But the 737 remains a fascinating bridge between the old world and the new.
Why would they keep the cables? Is it just because it is an old design they do not want to change? It seems like a lot of extra weight for a modern jet.
It is all about what we call type certification. If Boeing completely changed the flight control system to fly-by-wire, the 737 would effectively be a new airplane in the eyes of the regulators. Pilots would need much more extensive training to switch over. By keeping the mechanical feel and the cable system, they can tell airlines that their pilots who flew the older 737 can transition to the new one very quickly. It saves the airlines millions of dollars in training, but it also means you are flying a modern jet with 1960s era mechanical bones. It is like putting a Tesla screen and a modern engine into a 1965 Mustang.
That is wild to think about. You are on this high-tech MAX jet with fancy engines and huge screens, but underneath the floorboards there is a steel cable zigzagging its way to the tail. Now, Daniel asked about failover systems. This is the part that would make me nervous as a passenger. If the computer crashes or a wire gets snipped, what happens? With a cable, at least it is a physical thing. If the electricity goes out, the cable is still there. But if a wire loses power, is the plane just a brick?
That is the number one fear people have with fly-by-wire, and it is why the redundancy systems are so incredibly elaborate. In a fly-by-wire plane like an Airbus, you do not just have one computer. You have multiple, often 5 or more flight control computers. And here is the genius part. They use something called dissimilar redundancy.
Dissimilar redundancy. That sounds like a Herman Poppleberry term if I ever heard one. Explain that to the rest of us.
It is beautiful, Corn. It means they do not just use 5 copies of the same computer. If you have 5 identical computers running the same software, and there is a bug in the code, all 5 will crash at the same time. To prevent this, Airbus uses different hardware and different software. They might use 3 computers designed by one company using one type of processor, say an Intel chip, and software written in one language. Then they use 2 other computers designed by a completely different company using a different processor, like a Motorola or an AMD chip, and software written by a completely different team in a different language.
Oh, I see. So if there is a tiny bug in the software that only happens when you are flying north at exactly 300 knots while the landing gear is transitioning, it might crash the first 3 computers, but the other 2, having different code, will not have that same bug.
Exactly. It prevents a common mode failure. It is statistically almost impossible that 2 different teams would make the exact same obscure coding error. And beyond the computers, you have redundant power sources. You have the main engine generators, you have the batteries, and then you have the RAT.
The rat? Like the rodent? Please tell me there are not actual rats involved in the backup systems.
No, the RAM air turbine. It is one of the coolest pieces of emergency engineering. If a plane loses all engine power and all electrical generators fail, a little hatch opens in the belly of the plane and a small propeller drops out into the airstream. The rushing wind spins that propeller, and it generates enough hydraulic and electric power to keep the fly-by-wire system and the basic instruments running. It is a last resort, but it ensures the pilot can still fly the plane even in a total power failure. It happened on the famous Miracle on the Hudson flight. The RAT deployed and gave Captain Sullenberger the control he needed to glide that Airbus into the river.
Okay, that makes me feel better. But what about the physical space Daniel asked about? How do you fit all these backup systems into a crowded fuselage? He mentioned it is a limited space.
It is actually much easier with fly-by-wire. Think about it. A bundle of copper wires is much smaller and lighter than a set of steel cables, pulleys, and tensioners. You can run wires through tiny gaps, around tight corners, and you can easily shield them. In a modern fuselage, the wires are usually routed in separate paths. Some might go through the roof, some through the floor, and some along the sides. This ensures that a single event, like a localized fire or a structural failure, cannot take out all the redundant lines at once.
So by moving to wires, you actually freed up space and weight. It is like the transition from those old massive telephone switchboards to a modern server rack.
Massive amounts of it. On a large aircraft, switching to fly-by-wire can save over 2,000 pounds of weight. That weight savings translates directly into more fuel efficiency or more passengers, and it allows for much more complex designs. For example, on the Airbus A380, the giant double-decker, they have 2 completely independent hydraulic systems and a third system that is purely electric. Some of the actuators on the wings are electrohydrostatic, meaning they do not even need central hydraulic lines. They just need an electric wire, and they have their own little local reservoir of fluid and a pump. That would be almost impossible to manage with traditional cables.
It is like moving from a central steam engine in a factory with all those belts and pulleys to everyone having their own electric motor.
That is a great way to put it. It decentralizes the power. But Daniel's question about the mechanical systems of the past is still relevant because those systems had to be incredibly robust. On something like the 747, they actually had 4 independent hydraulic systems. The logic was that you could lose 3 of them and still have enough power to land the plane. The pipes and valves for those systems were built like tanks.
I guess the mechanical age was all about brute force and physical separation, while the digital age is about intelligence and distributed redundancy. But I am curious, Herman, do pilots miss the feel? You mentioned that in a Cessna, you can feel the air. In a fly-by-wire plane, is the pilot just moving a joystick that feels like a video game?
That is actually a huge area of engineering called artificial feel. Since there is no physical connection, engineers have to build in little motors and springs into the side stick or yoke to simulate the resistance of the air. On some planes, the stick will get harder to move as you go faster, just like it would in a real mechanical system. This is often called a Q-feel system, where Q represents the dynamic pressure of the air.
So it is haptic feedback, basically, like a high-end steering wheel for a racing simulator.
Exactly, but there is a funny quirk here. On an Airbus, the pilot's side stick does not move when the co-pilot moves theirs. They are independent. On a Boeing, even the fly-by-wire ones like the 777, the yokes are mechanically linked so that if the captain pulls back, the co-pilot's yoke also moves back. Boeing wants both pilots to physically see and feel what the other is doing. Airbus relies on electronic alerts and a light that says dual input if they both try to steer at once. It is a difference in how they handle the human element.
Wow, even the way they handle the human element is different. It is amazing how much thought goes into just moving a flap on a wing.
It really is. And to answer Daniel's question about whether we still see mechanical operations, in the world of general aviation, the small Cessnas and Pipers that people fly for fun, it is almost entirely mechanical. It is simple, it is reliable, and it is cheap. You do not need a triple redundant computer system to fly a two-seat plane over your house. But for anything carrying 100 people at high speeds, fly-by-wire is the gold standard.
So, thinking about the takeaways here. For one, fly-by-wire is not just about replacing cables with wires. It is about adding a layer of intelligence that can prevent human error. But it requires this incredible level of redundant engineering to make it safe enough that we trust it with our lives.
Right. And the second takeaway is that mechanical systems were masterpieces of engineering in their own right. The fact that we could control a 747 with cables and hydraulic valves is just as impressive as the software in an A350. It was just a different way of solving the problem of scale.
And third, the transition is still happening. We are still in this overlapping period where legacy designs like the 737 are flying alongside clean sheet digital designs like the A321XLR. It is a slow evolution because in aviation, proven is always better than shiny and new.
Absolutely. If it works and it is safe, you keep using it. But the future is definitely digital. We are even starting to see fly-by-light, where they use fiber optics instead of copper wires to be even lighter and totally immune to electromagnetic interference from things like lightning or solar flares.
Fly-by-light. I love that. We will have to do a whole other episode on that when it becomes the norm. Maybe in episode 1000.
I will start the research now. But seriously, this was a great prompt from Daniel. It really makes you appreciate the engineering that goes into every flight.
It really does. Next time I am in that seat 14B, I'm going to be thinking about those dissimilar computers talking to each other, and that little RAT turbine waiting in the belly.
As you should. It is what keeps us all in the air.
Well, I think that covers the basics and the deep dives for today. Before we wrap up, I just want to say, if you are enjoying these deep dives into the weird and wonderful world of technology and aviation, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps other curious minds find the show.
It really does. We love seeing the community grow. And a big thanks to Daniel for sending this one in. It was a blast to talk about.
Definitely. You can find more episodes and get in touch with us at myweirdprompts.com. We have the full archive there if you want to search for other aviation topics or anything else we have covered over the last 500 plus episodes.
This has been My Weird Prompts. Thanks for listening, everyone.
See you next time. Goodbye.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.